Today we're talking all about gears in robotics and mechanical designs and how you can make more reliable power transmission by making a nice, strong gearbox. I'm Brogan and I've been teaching robotics inside for over a decade now. And by the end of today's video, you're going to learn what a gearbox is, why it's necessary to have effective power transmission for things like robotics and mechanical projects, and then I'll show you how you can make your own custom gearboxes using some off-the-shelf parts and some concepts you might want to use if you're going to make your own custom gearboxes. So a fundamental problem we often run into in robotics is that we have access to a lot of motors, and typically motors spin really fast, but they don't have a lot of torque or force output. You kind of think of it like when you're using gears on a bike. You know, you can shift up in your gears to be able to go faster and have lower torque, or shift down in gears to be able to go slower but have more torque output to help you get up hills. We can do the same thing by building our own gearboxes for robots in our own projects. So taking an example of a good gearbox, you might have something like this or something like this. What constitutes of a good gearbox here is that you have your gears that are connected to each other in a non-cantilevered fashion. So when I talk about cantilevered, say the axle that the gears are running on is supported in two directions. These gears here are supported on ball bearings on both sides. There's a ball bearing under here. There's also a ball bearing up in there and another ball bearing up in there. So that as these sections ride here, they are very frictionless in their systems here. This is a system from GoBuilda and it uses a ball bearing based system. You can also have another system like so, where I have, again, that main kind of gear is constrained on 2 points. And then I have the other constrained against the motor that's pressed up right against. So even though this is a cantilever system, it would be really hard for this section here to actually face any cantilever on a section like that. So those are examples of good looking gearboxes. Now let's talk about an example of a bad gearbox here. This gearbox using GoBuilda's U-based channel system is not a good example of using gearbox because it's a cantilevered system. When I say a cantilevered system, is that this gear is only supported on one side. And particularly when we use these ball bearing based systems, is ball bearings themselves have a bit of play in them. So as we can see here, if we look right in close there, you can see that that ball bearing is able to push in and out of the hole that it's constrained in. If we look at this axle here, we can actually see that that whole unit is able to move backwards and forwards. And let's zoom in on the correct part. You can see that whole unit is able to actually shift. And what ends up happening is that as this thing is trying to turn, we can see that up over here, we actually have quite a bit of wiggle and play in those gears. So as they try to spin, it's less likely that they'll actually spin nicely. And what can also happen, unless this thing is fully pressed, it should be spinning nice and smooth, but because these gears are capable of twisting and rotating, it ends up making it so you get a not nice connection. So with gearboxes, having a cantilever system is typically a very bad idea. Now, to be able to construct a gearbox, there's a few different things that you'll need. You'll, of course, need your gears. And with your gears, if you're going to be using something from GoBuilda, as long as your gear teeth add up together to a factor of 120, it will fit on a GoBuilda-based system. So for instance, I have a 100 tooth and a 20 tooth. If I were to line these up together, line them up over those holes on the U-channel, the large 14 millimeters, they'll line up correctly. If I have a 52 and a 68, add these two together, you get 120. You'll notice that they also line up together over those holes. Then you'll need the actual gearbox itself. You can use a standard piece of U-channel as a gearbox. You could also use some slim pieces of U-channel, use a standoff, run in the middle here, and then you can sandwich these together to be able to make a gearbox like so, depending on what size it is that you need. This example, I'm just going to be using a standard piece of U-channel just because it makes it a little easier. You need some ball bearings. You can use GoBuilda's offerings, but this is a MF148ZZ ball bearing, and it is the exact same dimensions except that it is 4 millimeters across. Come on, pick me up. Except it's 4 millimeters across as opposed to 5 millimeters across, but it's a lot cheaper. It basically does the same thing. You'll also need some axles. And now you can use just a standard flush axle and then another point to be able to constrain it. Or you can use a steel axle here that has a retaining clip on it. I really like these retaining clip ones because what it allows you to do is it allows you to have something that will constrain this. Because in order to have an axle fit inside, you need to either have internally constraining it or externally. And in this gearbox, we're going to externally constrain this. So because I'm using 120, it lines up over 3 patterns here. I can put in one piece of ball bearing with the flange facing out. I'm going to use the steel E-clip first to be able to push through. Then I can grab the other ball bearing with the flange facing out again. And what I'm doing is I'm just holding my finger against this. And in order to make sure that my ball bearing actually connects that inner race, I'm going to use a little 8mm shim here. It's just a little 1mm piece of steel that allows us to only connect and contact to that inner race and not the outer race. So then I can take my other gear, flush it on. And what I want to do now is I actually want to push in against both, not too hard, but just very lightly, push in against the two. And this will allow me to actually start putting my gearbox together, tighten it that set screw. And I can now check that I have a nice frictionless system on this because I can spin this and it spins around quite easy. Now, what happens if you don't have something with an E-clip on the end to be able to hold this whole system together? What you can use is you can use one of these clamping collars or just a standard sonic hub. I'd like to lay this up with this clamping collar facing inwards, this little raised lip you can see on that section there, that one section's raised. And that basically acts as our own kind of little shim. So I'm going to slide that on, give this a little clamp. And now I have a way to constrain this. So I will put this always one hole in the middle, slide that through, slide through another ball bearing, again with the flange facing out. And now I'm going to paste my sonic hub in with a shim on top, and we will place that on like so. And we'll give this another clamp down on both sides. Again, making sure that I am clamping my fingers together. And now the last thing that I need to do is actually add on my gear. So I'll slide it on like so, and I have to add it in such a way that it's actually going to line up. So you notice that on one side with my gear, if I lay it down, if I put it thick side to the inside, I'm only getting about half a teeth mesh, which is not great. Instead, I'm going to lay it out on the outside here so I get a nice perfect mesh between those two teeth. And then here, this requires me to put in 4 screws. So I'm going to pop in 4 8mm screws onto my sonic hub. You might need to give a little rotation to be able to get yourself into those threads. I really like these hub-based gears as opposed to the pinion-based gears because it makes it a lot easier for you to build your own gearboxes up with more pieces. And it makes them a lot more modular, particularly when you're working on other robotics projects as opposed to just one. And now I have a nice, really strong system here that I can run along, and I'm not going to have much friction in the system because it's based off ball bearings. And I also have these gears, they're going to stay together rock solid that whole time. Now you might be wondering, if you've got a gearbox like this, how do you actually go about attaching a motor to one of these? You could attach a motor down in the end of one of these axles and shift it down a little bit. Another option you could do is simply gild a gearbox that's out on the side here. So I've got a motor here that's attached at the bottom of this U-channel, and I have a longer piece of U-channel with some sections built into it with these standoffs that I've used. And then I have just simply one through bore here. And this is a 48 tooth to a 72 tooth gear. And I've actually put in a little laser cut here to etch in what my teeth are. So this is actually a it's a 1.5 to 1 ratio. So I actually end up with about 4,500 RPM as opposed to the 6,000 and about 0.158-ish Newton meters output here as well for about a 1.5 reduction on top of what I had before. And this can be a really useful way of attaching and making a gearbox for a system that allows you to use it in a more modular way on different robotics projects. So most motors that you buy are typically fixed RPM and fixed torque as well. So for instance, this motor here has about 6,000 RPM and about 0.105 Newton meters of force. But you can also get some of these, like this HDX motor, that allows you to add gearboxes built in, which is really slick. So what you can do is you can take that top part off and you expose the spur gear, and you can clip in one of these gearboxes, and sometimes they can be a little bit finicky to actually clip in. And now when I clip this in, I've actually taken that same gearbox and I've actually reduced it to a 5-to-1 ratio. So instead of having 6,000 RPM, I'm now sitting at about 1,200 RPM. And instead of having 0.105 Newton meters, I now have about 5.25 Newton meters. Now that does assume 100% efficiency and all those things, but it's quite nice. What you can also do is you can also stack multiples of these on top of each other. And what that lets you do is rather than having a 6,000 RPM at a 1-to-1 gear ratio, is now I can actually have a 60-to-1 gear ratio, output 100 RPM at the end, and have about 6.3 Newton meters. So I actually have 60 times the force, roughly, than what I did initially. So you can have gearboxes that are actually built into the motors themselves, as well as have gearboxes that you are making externally, like so, to be able to reduce these. Now, this is a 5-to-1 reduction. This is also a 5-to-1 reduction. I hope you found that a helpful tutorial on the concept of making stronger gearboxes, what a gearbox is, and why you should definitely use one when you're talking about power transfer. If you're looking for more robotics resources, things like CAD files, things like code snippets, things like that, or you just like what I do, you can consider joining my community down below. Let me know in the comments if you've got any questions about doing things like this. I'll try my best to answer them for you. And as always, best of luck with building your next robotics project.